All right, continuing on with week 1 of vibrations. Here's another example. This again is from Dr. Bob's notebook. Notes to accompany this right here. So there you go. So let's say that we have this connecting rod, and we want to find the mass moment of inertia about its center of gravity. Like, how would we go about doing this using the principles that we're learning about in vibrations? Well, let's start out by making an FBD and an IBD. And we will rotate this thing a little bit. And we're going to make some assumptions along the way. It looks like a chicken wing. So we'll try to make the second chicken wing look a little bit like the first chicken wing. I'm not sure I did a great job with that, but we'll set those things equal to each other. And we will support it. I'm showing it supported here. I'm just going to make that approximate to the middle right there, right? So I didn't mean to make that. So am I going to, I won't erase it. I'm going to go, here's my reaction forces. We'll go RAX, RAY. The only thing I have here is a MG. I'll use lower green here to draw it that way. And see, I should label the angle. I guess I can label the angle right here. Oops. I think I'm going to get this wrong. Okay. Alright, so here's the angle that thing's at, theta, which is also that angle, theta. Anybody else notice it? Right, so here's our accelerations. I won't bother with the normal acceleration. Let's just say that we have IA. It's about this times. I usually we go alpha. We go alpha right there. All right. That IA means it's the mass moment inertia about A, not the center of gravity, right? So we're out to find this mass moment inertia about the center of gravity. So let's do our stuff from the sum of the moments, our stuff from dynamics. It's going to be about A, right? So we didn't have to do the effective moments thing. We did it because we're gonna do it about this about the rotation point right there. So looking over to the left hand side, the only thing we really have. Oh, and by the way, we had. I'm gonna call this just R. That distance. Yeah, and so here's R right here. That distance. So we're going to take the sum of the moments, and it looks like we're going to have a negative mg, and it's going to be times r times the sine of theta. And that's going to be equal to, all right, so IA, we use the parallel axis theorem, right? And we note that we drew it as going counterclockwise, so it's going to be positive. And we'll use the parallel axis theorem plus m times r squared right there times theta double dot, which is the same thing as that alpha, right? And we'll also go ahead and say, well, let's just only do it for small angles. And you go, well, what constitutes a small angle? You could try it yourself to try to see how much they start to diverge as they go there. But like somewhere around 5 degrees is probably okay. I think it's somewhere around 7 degrees where they start to diverge would be too much of an unacceptable amount. But you can try it out yourself and see. So we can rewrite this thing around and go I plus m times r squared theta double dot plus mg r theta equals 0. And of course, theta double dot plus mg r, oh, not theta, sorry, stop, divided by I this plus mr squared theta equals 0. And therefore, you can find that the natural frequency of this is going to be the square root of mgr over I bar plus mr squared. So the frequency 1 over 2 pi be the square root of mgr over I bar plus mr squared, which remember is 1 over the n, and you could solve for I bar. Did I want to bother doing that? I don't know. I guess I could. You want to flip this upside down, right? There's no problem with doing that. And then you square it, and you're going to multiply the other side. So you get tau n, that's what you measure, over 2 pi. You would square it, and that should be I plus m squared. I didn't mr squared, sorry. Over mgr. So I bar is going to be tau n, I'll just keep it together, 2 pi squared mgr plus mr squared. So if you were to measure with a stopwatch or really quick video analysis of the thing and be able to get the period of this, we'd be able to estimate what the mass moment of inertia of the object is. Or we could just build it in SolidWorks and there you go. Same, right?